So this is the second in the series of discussions about process virtual memory. The next discussion, if I remember my slide sequence correctly, is design guidance for the Pintos Virtual Memory Lab. If it is not Monday, it will be Wednesday. It's going to be one of those two. So since the virtual memory system is the least implemented part of Pintos, it says implement virtual memory in this directory. You go to the directory and it's empty. So you have to figure out what you are going to do. And it's a good exercise. It's good to be able to create things from scratch. But at the same time, you need to understand what you're trying to do. So we have some good material about that. And hopefully you'll find it steers you well as you go through the virtual memory implementation. But today we're going to go ahead and continue talking about virtual memory. So we talked about it last time for the first time officially, even though we've been talking about it all along, informally in other circumstances. The reality is that whether you're the kernel or whether a user process, the program that's running is emitting virtual addresses that are translated by the CPU into physical addresses that access main memory. So you have no idea because the abstraction is so clean and well exposed inside the processor. But if you were watching the addressing pins on the processor with a digital logic reader or something like that, you would see different addresses from the addresses your program is emitting because of this logical to physical address translation. So we do all of this for a couple of reasons. Yeah, so blah, blah, blah. We talked about all of that last time. I also want to certainly encourage you to look at the slides that talk about inverse page tables and hashed page tables. There's all kinds of different ways that this has been done. So the way that we do it right now is with hierarchical page tables. Okay. So yeah, we have virtual and physical memory divided into uniform blocks. All of them are called pages, but really we try to call the physical memory blocks frames because it's just a place to hold some data. And if different processes are using that frame, they'll be putting different pages into it. So that's why it's nice to have this distinction in the language when you're talking about this stuff. Yeah, so how do we manage the mapping? So this is what I got ahead of myself. We do this with hierarchical page tables with virtually all modern processors right now, at least that we use day to day. If you have a really fancy pants 64-bit addressing space processor, then it's probably going to do something a little bit different because we talked last time how the hierarchical page table mechanism doesn't scale well as the address space size increases. So that's the challenge there. Okay. There are multiple benefits. We talked about that last time as well. Address space isolation is a huge one. Very, very important. This is why even mobile phones, even though they don't have swap devices, still implement virtual memory so that they can have address space isolation for different apps. And it also simplifies the application binary interface. But today we're going to talk about swapping because this is the big benefit of the virtual memory abstraction in a general purpose computer. It allows us to overcommit memory to programs. We can have more processes running than maybe we have physical memory to support. Hopefully you understand what I mean when I use that phrase. The important detail here is that programs don't use all of the memory in their address spaces all at once. They just don't. If you have a program that is huge, then maybe you're running in 20% of it most of the time. So that's 80% of it you don't need in memory. If you're working on the heap, you have big complex data structures. You may not be working in all of those data structures all at once. You may have allocated a small fraction of your heap that was given to you by the operating system. So why allocate physical page frames to those parts of the process's address space? So since this is the case, we can use this virtual memory abstraction to run a lot of processes and present the abstraction that memory is much larger than it really is. And everybody wins. Okay, to be able to move pages back and forth between memory and disk or whatever the backing store is, we need some way of keeping track of when an entry in the page table is not referring to something in memory. So we need a way of saying this virtual to physical mapping isn't currently valid. And so we just go ahead and introduce a valid bit that when it's set, we know that that entry contains a virtual page to physical page frame mapping. Okay. Now, as the picture indicates, the mapping is a simple array index mechanism. So you take the virtual page number and use that to offset into the table from the start of it, which is in the page table base register. And we can change this every time we do a context switch. If you look at Pintos, that's exactly how it works. It switches to another page directory when it is getting ready to enter back into user space. If it's doing a context switch, I should say. So anyway, virtual page number, lookup, and then the MMU can look at the valid bit. If the valid bit is 0, then that means there's no mapping. And so this is where the term unmapped virtual memory comes from. The entry is invalid, so the MMU can't do the address translation, and therefore it raises a fault. So so if the valid bit is 0, the rest of the entry is ignored because the MMU is like, I don't know what it means. I can't do anything about this. Okay, let's see. So it'll look at the valid invalid bit. This is what I was saying. If it's valid, it will handle the address translation all by itself. If it can't, this is where the MMU, the processor and the kernel work together closely to resolve the fault. So trap into the kernel. And I think I have a couple of examples here. So this is a page table with 8 entries. Nice simple world that we live in here. A normal page table in IA32 has 1,024 entries, and of course we have 2 layers of those. So you can see that we have 4 physical page frames. So we only have room in memory for 4 pages of data. But our page table allows us to have a virtual address space that includes 8 pages. And then we have a backing store which holds versions of pages that are not currently in memory. So you see some virtual pages are in physical memory. So the page table says PTE1 or page table entry 1, 2, 4, and 7 are all in physical page frames. Some virtual pages are only in the backing store. Notice it's the valid bit is 0, but there's some other value in the rest of the page table entry that somehow the OS interprets as it's right here. And same thing with page table entry 6. It's not valid, but the OS knows somehow that the page's contents are actually stored on the backing store instead of in physical memory. Okay. So 2 virtual pages have not been allocated. You can see PTE0 is currently invalid, and also the address or whatever the value is, the OS knows this means it's unmapped, and same thing with PTE5. Okay. So if the program were to access a word in virtual page 2, so anywhere in there, remember there's a virtual page number and a virtual page offset. The offset goes straight across because the page and the frame are the same sizes. Otherwise, that would be crazy. So the virtual page number is used to index into the page table. And so we can go ahead and look and we see PTE2. Hey, it's valid. And hey, the physical page number is page frame 1. So the MMU can go ahead and take care of that entirely on its own. The kernel is not involved at all because the MMU went and did the lookup, saw that everything was good, did the translation, emitted the address on the address bus, either read or wrote the data in that page. So hopefully that makes sense. Now let's access a word in virtual page 6. And you'll notice here the MMU will do its automatic thing and it goes down to PTE6 and says, this valid bit is 0. Now, that's as far as the MMU goes. It says, is the valid bit 0 or 1? If it's 0, it just says, I'm out. It doesn't care. It doesn't handle the swapping in or out. It just says, kernel, this is your problem to solve. And so the kernel steps in, and the kernel can look at the information it has and say, this virtual page is actually stored on the backing store right now. So I can move it into a frame, and then we can retry that instruction and it will succeed. And so that's what the OS kernel sets out to do. The only issue is you look at your, because we have a universal picture of the computer right now, we can look at our physical memory and we say, there's no frame available. All the frames are in use by other virtual pages. So now the kernel has to figure out which page to evict out of its frame so it can free up a frame, and then it can move virtual page 6 into that frame. So it selects a victim page, and I don't know why sometimes the terminology used in computer science is either exciting or macabre or lurid or whatever, but here we go. So we have to pick a victim page to evict, and you can see here that we've chosen virtual page 4. Why? Well, we'll talk about how we would make these decisions in a future discussion, but for whatever reason, the kernel chose virtual page 4. Now, the kernel can go in and say, hey, has that page actually been changed? Because if it hasn't been changed, it may not want to actually incur the cost of saving it back to the backing store. If it has changed, then it needs to do the right. And as the slide says, disk accesses are slow. I hope I've given that impression all the way through so far in the discussion, that a disk access, even to a solid state drive, is on the order of 100,000 clocks, and an access to a slow spinning magnetic disk is going to be on the order of tens of millions of clocks, maybe with a cap of 30 million clocks. That's a lot of program you can execute while you're waiting for the data on the disk to show up. So what we do is we extend our page table to record whether or not writes have actually occurred to a particular page. And once we can record that writes have occurred to a page, then we'll know if the page's contents are dirty and therefore need to be saved, or if they are unchanged since the last time we loaded them from the backing store, and therefore we don't have to save the page again. That would be great. If anybody has any questions, make sure you ask them, because this is going to be all extremely important for you in the next project. Okay, so virtual page 4 is evicted. You can see it's written back to disk. So this is what the kernel has to queue up and make sure that it's done. Now, once that is done, or maybe before, because you'll have to work through the details of what order you have to do these things in. But the kernel needs to update the page table for the process to record that that virtual page is no longer in physical memory. So it goes in and it sets the valid bit to 0. And if the kernel uses the rest of the page table entry to store where the page is stored in the backing store, it'll update that as well. So you can see that represented on the slide. The arrow is pointed down to the location on the backing store, and the valid bit is set to 0. Subsequent accesses to virtual page 4 will generate a fault. Okay, but now we have an empty frame, and so we can go ahead and load virtual page 6 off the backing store into the page frame 3, and we can update the page table entry to point to that physical page as well. Now here's the cool thing. We ended up in the kernel because of a fault, and faults are interesting. They're instructions that failed but may be able to succeed if the kernel can do some work on the side. And in this case, that's exactly what happens. When we return from the page fault handler, the CPU knows, go back to the faulting instruction, try it again. And so it will rerun the faulting instruction. This time, the MMU looks up in the page table and says, there's a virtual to physical mapping for page table entry 6. So it goes ahead and emits the physical address in page frame 3 to perform the memory access. So that's a simple walkthrough of what is happening in your computer and in your cell phone and on your Raspberry Pi all the time. Okay, one interesting issue with these dirty flags, And there's another flag that's also maintained on IA32. It's called the accessed bit. So IA32 has present, which is equal to the valid bit on these slides. So IA32 has present. Is there a mapping present in this slot? Dirty, has it been written to? And also accessed. Has it been read or written to since the last time it was cleared? And so you have to be really careful with these. You can see in this example, you have two processes, and they're actually sharing a physical page frame. They're both sharing page frame 1. Notice they're mapped to different locations in each of their address spaces. So process 1 has it in virtual page 5, and process 2 has it in virtual page 1. Perfectly fine. Shared memory is the fastest way for processes to share information with each other, but it's also very challenging to do because exactly as this picture indicates, the shared memory may be mapped to different address ranges in the two processes. So you have to design your data structures to not depend on pointers, because a pointer that's valid in one process's address space may be invalid in the other process's address space. So you have to be careful about that kind of thing. But anyway, look at the dirty flag, because I want you to think about when a process writes to a page, the dirty bit is set by the MMU for the actual virtual page that was accessed. So in this case, when we have two page table entries referencing the same physical page frame, it's only the process that actually does the write that knows that the page is now dirty. So multiple virtual pages can map to one physical frame, and the MMU only sets the dirty flag in the PTE that was used for the access. So other ones in other processes that weren't the writer won't have their dirty bit set to 1 for that page. Okay, so process 1 writes to virtual page 5, so we get an update. So you'll notice there's a little D now on the right array of page frames because it is now dirty. And the dirty bit on PTE 5 in process 1 is set, but process 2 doesn't actually have it marked as dirty. The MMU is not clever enough to know what are all the page tables that the operating system has maintained. So this is something the OS has to deal with. Okay, so if the kernel later decides to page out process 2's virtual page 1, hopefully you'll look at this and say, wait a minute, process 2's virtual page 1 is also shared by process 1. So now the OS needs to be clever, and it needs to know that this page is shared and who all is using it so that it can go and look in those page tables as well to see if the page is marked dirty. Okay, so the virtual page is dirty from earlier write, but process 2 does not have that represented in its page table. So this is called aliasing. I mean, aliasing is a term that's used in a lot of different contexts. We even use it in CS1 to talk about passing object references to different pieces of code and have two references referring to the same object and all of these kinds of things. But in this case, it can be a little bit tricky because the kernel has to know that a particular frame is being used by multiple processes. Okay. So the kernel, when you have a shared page, then the kernel has to go through all the processes that share that page. And it needs to check all of their page table entries. And you may say, that sounds complicated. And I suppose it's a little bit complicated. It's just like all the stuff inside the kernel. You just have to keep track of stuff. But it's not anything out of the ordinary, because if you're going to evict the page in frame 1, you have to tell all the processes that think it's present that it's no longer present. So the kernel has to go through all these page tables anyway to make sure the shared page is now marked as not being in memory. Okay. So Linux has some clever mechanisms for this where there's an additional set of data structures and processes that share a page form a linked chain. I'm sure that's a shock to everyone, but there will be a linked chain of processes that share a given page so that the kernel can go through and update each process's page table to say this shared page no longer in memory. And it can also at the same time check if anyone has written to it. So it's kind of an important detail. All right. Why am I talking about this? Well, there's two reasons why I'm talking about this right now. The first one is that Pintos has an extra credit item of sharing pages between processes, but it's extra credit. Furthermore, I believe that the pages that are shared are read-only pages, so I don't think you have to worry about shared read-write pages. So fortunately, this is not a problem that you have to think about in the context of Pintos shared memory. But you still need to be aware of the general issue. The second thing about Pintos is that aliasing does in fact occur all the time, because Pintos always maps all the physical page frames into the first part of the kernel memory. So remember how we have a kernel address space, which is the top gig of the virtual address space, and then the user process has the bottom 3 gigs. Well, to make Pintos easy to work on, the Pintos kernel simply maps all the frames into the first part of the kernel address space. So the kernel always sees all memory, and it can access everything, and it can do whatever it wants on behalf of any process. So that presents a challenge, because a page or a frame will be mapped into kernel space and also into user space for some process. And so that is also aliasing, and you'll have to think about that. That's one of the things that the Pintos Project 4 write-up specifically mentions. And so you can think about it in this context. The solution is really simple. It's basically always use the kernel page table entry to do the writing, and then leave the user page table, or don't write to the user address space, because that'll set the dirty bit on the PTE, and it's like, so it's not too hard to figure out, but you should still be aware of this issue of aliasing. Okay, so hopefully that'll help in a few days when you've recovered from Project 3 and are ready for Project 4. Now, because we have this paging mechanism and swapping mechanism, we can move parts of a process in and out of memory, which means that we can do things on a much finer grain than standard swapping would allow. Remember that standard swapping is moving an entire process in and out of memory, and if you have a large process with lots of memory in its virtual address space that it's using, that's going to be slow. So paging is so much better than swapping. The way that this often works in operating systems is using this mechanism called demand paging, which basically we only ever let a process have a frame for a page once they've actually tried accessing the page. If they've never accessed the page in their address space, why ever allocate a frame? Hopefully that makes sense to you. So that's why it's called demand paging. We hand you frames for your pages on demand, and not a second before. So if you were to do this with a program that was stored on disk, and this is what you'll get to do in Project 4. This is one of the tasks for Pintos Project 4. Right now, the way that Pintos works is it just sucks the whole program off the disk and plops it into virtual pages in the process. So it's doing all that loading and copying into the virtual memory. Well, what we could do instead is just set up the page table so that all the page table entries reference the corresponding parts of the program binary, but none of it is in memory. And so what this means is that we will only load the parts of the program that ever run. And this is kind of neat. So the process begins running. Remember, we start at 804, 8000. We do our first instruction fetch. And there's nothing in that virtual page because we haven't actually loaded the program into memory. So we get a fault. And the fault handler goes and says, this chunk of memory is supposed to be the first 4 kilobytes of the program. And so the page fault handler sucks the first 4 kilobytes off the disk, sticks it where it needs to be in memory, and then lets the program start executing it. When we finish running that page of the program, we exit it, and the next instruction fetch will cause another fault, and the next page of the program is loaded into memory. So you can see how demand paging only loads the parts of the program that are necessary as they are necessary. So it's a really nifty kind of mechanism for making sure that every process has only the amount of physical memory that it needs. I hope that makes sense, because that's what you get to build. Okay, let's see. Yeah, here's another one. Memory heaps are a great example of this, because you can go in and say, hey, I'd like to make a 10 gigabyte memory allocation. You can do that now that we have 64-bit operating systems. I'm not used to this. I grew up in a world where the system memory was measured in megabytes rather than gigabytes. In fact, I think my first computer had 1 megabyte of RAM, and that's all it had. So, but nowadays, no biggie. You can say, I'd like 10 gigs of RAM. My laptop here has 32 gigs of RAM. It should be able to satisfy that very easily. But the way that the kernel will often handle these things now is to just update its address space map, saying, hey, the heap is now 10 gigs larger than it was before. But all the virtual memory pages in that range are invalid because none of them have been accessed. Why allocate frames to the process if it hasn't accessed any of those pages? So as the process interacts with the heap, then the kernel starts allocating frames into those corresponding pages so that the program can actually read and write memory and do stuff. Okay, so that's the idea. And if the process's heap needs to grow, I decide I need another 10 gigs for some reason, then the kernel can update the address map for the process, but it won't necessarily allocate frames until it knows that they're actually being accessed. So this is the beauty of this kind of a mechanism. Okay, yeah, so that's what I say here. The kernel will only allocate as many virtual pages to the heap as are required by the program. Okay, let's see. Yeah, so at some point we run into the sad scenario where you run out of frames. And this is actually one of the suggestions for Project 4's implementation, is that you build your page allocation mechanism first without worrying about page eviction, because you will be able to run tests until they run out of virtual pages, and then it'll just die. And that's okay, because some tests will pass and you'll be happy because some things are now working. So, you know, at some point though, you have to figure out how to get frames available because all the frames were in use. And so, this is where the kernel has to have some policy called a page replacement policy or a page eviction policy. And this is a great example of the separation of policy and mechanism, because the mechanism is go do junk on the disk. How do I have my backing store structured? I don't know. It's part of the mechanism. How do I manipulate the page table? That's mechanism. Policy is how do I make the decision of which victim page to evict so that I can free up a frame to use for some new page. Okay. So, we'll talk about that a lot more. I have, I think, 2 lectures. I can't remember if I have 1 or 2, but I go through quite a number of policies. And fortunately for you, you don't have to implement a particularly complex one for Pintos. You basically have to do something that approximates LRU, and the common approach that is recommended is called clock. And clock doesn't really require much sophistication. You can do clock without any timer interrupt. You don't need a timer tick interrupt for that. You can just update the state of the replacement policy every time there's a fault. So not too bad. Okay. Also, there is this thing called pure demand paging. So demand paging is I only allocate frames to processes when they're, you know, the corresponding page is accessed. Pure demand paging is like we only ever do that, because a lot of times what kernels really want to do, pure demand paging, while it may be the most minimal approach because it minimizes the number of frames I require to satisfy a set of programs' needs, it's not as fast. And if we know certain pages are going to be used right away, why not load them? And so prefetching is a very common technique in operating system kernels. For example, I mentioned we could just set up the program so that the first page of the program text generates a fault and then we load it in. Why not just load it? We know we're starting at that page, so just load it. Same thing with the stack. If I know that pushing stuff will immediately generate a fault when the program starts running, why not allocate a page for the stack? And so I think these are some of the suggestions in the Pintos write-up. At the very least, it suggests having a page for the stack, but stack growth will be something you implement in Project 4. But it may suggest pure demand paging for loading the program binary. So you'll have to see all of that stuff yourself when you get into it. Okay, another cool technique you can implement called copy on write. So copy on write is a mechanism for efficiently handling the sharing of information or the sharing of state across multiple processes, or you can implement copy on write in other contexts as well. It's certainly not only in this specific context I'm going to talk about. Process forking is a super common place where this appears. You have the parent and it forks and now there's a child. Now the child is supposed to be an identical copy, but the parent and child can diverge in their state as they run. The parent can manipulate its state in one way and that's isolated from the child. The child can manipulate its state in another way and that's isolated from the parent. Okay. So, so this is what I say here. Parent and child execution begins to diverge and their state starts to diverge as well. Old versions of Unix were really slow with forking. They were slow because forking was implemented as actually making a copy of the process's address space and contents. And even when processes were small, when system memory was measured in kilobytes as opposed to megabytes, forking was very slow, and people thought that this was going to kill the Unix abstraction until copy on write was devised as a technique. So what copy on write allows the kernel to do is to share the pages between the two processes. Now, of course, if they're shared, then that means when one process writes to a shared page frame, the other process is going to see the mutation. So they're not isolated anymore. So we have to be a little bit more clever than that. And so as I say on the slide, if the pages are shared, they can't be written to because we would have violated isolation. And so what the kernel does is it goes in and marks those shared pages as read-only. Because they're read-only, if a process tries to write to a page, the MMU generates a fault. It's a protection fault in this case instead of a page fault, because you're violating the access constraints on the page. Okay, so the process tries to write to a read-only page. So you have parent-child, they fork, they share a bunch of page frames, and they're all marked read-only. And so one of the processes tries to write to one of these pages that's read-only. So then the kernel can say, this is a copy on write page, and it can go ahead and make a copy of that specific page and give it to that process so that that process now privately owns it. And it can write to its heart's content. Nobody else will see it. Okay. As I say on the slide, if you only have one process sharing a copy on write page, it becomes a no-op. The kernel just sets the page's access mode to read write, and then it goes on. Okay, so kernel updates the process's page table. So we say we tried to write to a copy on write page. The kernel says, and it makes a duplicate, and then it updates the process's mapping to point to the copy. And then the faulting instruction will succeed. Okay. Now this was sort of revolutionary for fork, and made fork really manageable as far as, being an abstraction for Unix processes. Okay. Now I do want to mention, because even like when you fork a process, you're still duplicating page tables, right? The parent and the child still have their own page tables, and the address space mapping has to be copied and all of this stuff. And you may say to yourself, that's still too much work. And so there's another system function called vfork, and vfork does the fork, but the processes share the same page table. Okay? Like I say here, if we're going to fork and then exec, maybe you remember that from the first project because that's how command shell works. I fork and then I exec. So if I'm just going to exec, which means I'm completely replacing the process's address space map, then I can use vfork instead of fork, and it will not create a copy of the original process's page table. So this will be faster. So it's also scary because this is a way for a process to fork and then have its child blow its brains out. Because the child and the parent will see exactly the same memory in the exact same state, and they'll both be able to manipulate it, and chaos will ensue. So, so in this case, you want to make sure that if you use vfork, that it's immediately followed by an exec. Okay, hopefully that makes sense to everybody. If anybody has any questions, please put them in the chat or ask them. We'll be revisiting these topics over and over, though, so hopefully it'll help to familiarize you with how virtual memory works, because it's going to be extremely important for the next project. Okay, the next thing to talk about is memory area descriptors. One of the things that I want to mention is things like copy on write. The MMU, the memory management unit, has no idea. Oh, I see a question. Why exec right after the vfork? Well, the reason why you exec immediately after the vfork is because you're running a separate program, and the address map, the virtual address map, is going to be taken from that program's binary. I suppose you could come up with a scenario where you vfork without execing, but it's probably a horrible idea. So hopefully that answers that question. Okay, things like copy on write are not comprehended by the MMU. The MMU is very simple. Remember, the memory management unit understands the valid bit, and it will update the dirty bit, and we haven't seen it on the slides yet, but it will also update the access bit. That's all it knows. It knows how to do address translation. It doesn't know about copy on write. It doesn't know about other clever abstractions that people build in kernels. And so almost always, the kernel needs to maintain additional information beyond what the MMU has. So you have to think of it as the CPU has its understanding of the address space map, and the kernel has some higher level abstraction representing the address space map. We almost always have to have both of those things. And so as I have on the slide, this is oftentimes called a supplemental page table, and that's what is called in Pintos. One of the things you'll see when you read about Project 4 is supplemental page table this, supplemental page table that. Well, this is the information the kernel tracks so that it can do all the clever stuff that it does. And hopefully you'll see why this is necessary pretty quickly. What I have on the slide right here is what Linux does. We have PGD, and so like I say here, I'm just going to throw these things up here, but PGD is the page directory. So that's the top level of the 2-level page table hierarchy on IA32. Remember, it's a 4-level hierarchy on x86-64. Fortunately, we aren't living in that universe right now. So PGD is the process's page table. That's what the MMU understands. That's what's loaded into control register 3 when we are exiting from the kernel and context switching to a new process. Then you have mmap, and mmap is the kernel's version of what the address space map looks like. So this would be what is called the supplemental page table. And you can see how it's got all these details describing different chunks of the address space. So you have VM start, VM end. That's the actual range of addresses that that entry corresponds to. What are the protections on that memory? What are the flags on that memory? Is it copy on write? Is it read only? Is it shared? You know, you have all these different things. And then, of course, these are chained together into a linked list so the kernel can This is all used by the fault handler. I'll show you how in a second. Okay, so yeah, this is what I was saying before. This is from Linux 2.6, so this just sort of gives you an idea. Task struct is the top level Linux kernel process data structure. And so there's an MM thing in it that represents the memory map, and it has one version for the MMU, the memory management unit on the CPU, and the other is the higher level abstraction that the kernel understands. Okay, so I already talked a little bit about this stuff. We have this higher level description of the virtual memory regions of the program. Okay, let's see. So VM start, I already talked about a lot of this stuff. Now, here's the thing that I want you to understand, because this is super important. When you have a normal memory access, and what I mean by a normal memory access is the user program is running, you read your variable, you access stuff on the heap, and your program is correct and working properly, right? And so there's no like dereferencing null or something like that. It will, the instruction will have a virtual address. The processor executes that instruction. The memory management unit gets that virtual address, uses the page table to do the virtual to physical mapping, and sends out the address, gets back the data. Okay? Notice that the higher level page table information is not used at all. The CPU is able to do this entirely unsupervised, and it just uses the page directory. Okay? Now, when we have a fault, we can have different scenarios. And the different scenarios can only be differentiated by looking at the higher level information we have in our supplemental page table. Are we doing a read or write in the data section, which would be fine, but maybe there's just no frame allocated? Or are we trying to do a read or write to an unmapped region of memory? We need to be able to differentiate between those. What if we try to do a write into the program text that's binary code and we don't want to allow writes because our operating system doesn't suck? We need to be able to differentiate between these different causes of faults, and the way that the kernel differentiates between them is by looking at the supplemental page table information. That's how it can say, this fault is normal, I can resolve it, or this fault is abnormal and I have to terminate the program, or send a signal which will usually terminate the program. Okay, MMU raises a fault, the page isn't in the process's address space. So basically, the important thing to understand, and I think many of you have probably seen this because you've worked in the fault handler by now, the fault handler gets the address that was being accessed. And so it can use that address to walk through the list of VM area structs, or whatever equivalent you come up with, and it can look at whether or not the address falls within a particular range of addresses. If it gets all the way through the entire list and finds no virtual memory area corresponding to that address, it's like, okay, that was just la-la land. That was the process being crazy. So we send a sig-seg-v to the process, and the default behavior of that, and probably should always be the behavior of it, is terminate the process. Okay? So let me see. Yeah, so this is represented by this arrow up here. I have this access way out in la-la land. Walk through this, can't find that address in any of the VM area structs. The program's being kooky. Let's just kill it. All right. Now we have an access. We know it falls within some VM area struct. So we know it does correspond to some part of the address map, but we just need to figure out how to resolve it. So you have, in this case, you can see an access into the data segment of the program. And so if you have a situation where the page is swapped out, then the kernel can load that page in and update the page table for the process and retry the instruction. If it isn't allocated, the kernel can simply allocate a new page for that process. There's a couple of different sources of information, and I talk about this in subsequent slides. You can either map a file into the virtual address space, or you can map something called, what is it called? The anonymous file is what it's called. It's a file full of zeros, and when you map the anonymous file into a page, it clears its contents. So you'll have to do something like that in Pintos as well. Okay. All right. If we have a situation where you get a protection fault, then you know that the MMU was unhappy, but you don't know that it was wrong. You have to check the supplemental page table information for that. Here I have an example of a write to a read-only page. And so it can go through and say, does this fall within a copy on write virtual memory area? If it's in a copy on write virtual memory area, it just does the whole copy the page and point the page table at the new page and make it read write. Life carries on. If the memory area does not allow writes because it's program text or something like that, it's supposed to be read-only, then the kernel can again queue up a signal to the process, which is usually a SIG-SEG-V. Unixes map both page faults and protection faults to the SIG-SEG-V signal. So that's the situation there. Okay, let's see. What else do we talk about? If the memory area does allow the operation, the kernel carries it out. Let me see. Oh yeah, copy on write. So I already talked about this. Copy on write, it can just duplicate the page if there are multiple processes sharing it. If it's only one process sharing it, then it can go ahead and just set it to be read write and update the page table and let the instruction re-execute, and it should run. Okay, hopefully all of this is starting to help you get situated on how virtual memory works and how we can build this really clever and powerful abstraction. So, like I said, I'm not precisely sure what we'll be talking about next time. I'll have to look at the slides, but we will either continue exploring how you build this whole abstraction, or we will have the Pintos Project 4 orientation. And I'm pretty sure that's the one that we'll be having next, is the orientation, since Monday, I'm hoping people will begin thinking about the implementation, because that one is definitely, the last two labs, unfortunately, are harder than the first two Pintos labs, and they really require the full 2 weeks. So you need to make sure you start those early. Let's say start them on time. We'll call it that. So, all right. Well, I make sure I advance to the next time. I hope you all have a good weekend. Let me see. Is there a question here? How is the kernel able to handle all of this memory valid check and allocating page tables during copying without compromising performance? Well, it only really does it when it has to. And there's a lot of little tricks that it uses. Like, let me go back to the VM area structs. I'll just talk about this really briefly. These VM area structs are kept in order so that the page fault handler knows when it can stop searching. Also, oftentimes, like, you have two possibilities, right? A fault will either be because the program was bad, and it'll probably take a few hundreds or a few thousands of clocks to realize that the program was bad. And then what's happening to the program anyway? It's terminating. We'd like that to be an uncommon scenario. We would like our programs to not suck. So not a huge performance overhead if there's something like searching through a linked list that has addresses in order. If it is something that actually is a valid access, almost certainly what you have coming next is a disk read, a disk write. So something costing a few hundred more clocks is not really the part of the picture that's slow. And so you can just go ahead and do it in a way that is reasonable, but not as fast as absolutely possible, because it's not actually going to save you a huge amount of time over the long run. And you might as well just have it be more coherent. Now, that said, the Pintos supplemental page table, the nice thing about Pintos is you only have to worry about, I think, 64 megabytes of RAM. I think that's the cap on how much Pintos is able to allocate. So because of that, you can actually have a supplemental page table that is an array, as opposed to a list of structs. And since you can have an array instead of a list of structs, it'll be a lot faster to access. So I think the more interesting question is actually the space overhead, because maintaining these additional details about the address space takes up memory. And so you have to ask the question, is the trade-off worth it? Like, am I getting enough benefit from this extra information I have to maintain to make it worth offering these additional abstractions to the user? And so we'll talk about that as well in the future. It turns out that supplemental page table information tends to take a very small fraction of the total physical memory space. And so it's very, very much worth retaining. Okay, so great questions. Hopefully this was all helpful, and I will see you on Monday.